Alrighty, here we go. What we're going to go through in this video is section 8.3.1, which is all about rational functions and their graphs. Kind of a fair warning, there's going to be kind of information overload in this video, so I'm going to move pretty quick just so it isn't 30, 40, 50 minutes long. That's probably a little bit of an exaggeration, but either way. Our EQ is how can I identify points of discontinuity in a graph. And we're going to learn a little bit of vocab and a little bit of new stuff today. So as a quick little warm-up, going back to 8.2, which was all about reciprocal functions, I'm curious as to what equation formed this graph, or what equation made this graph. So how I'm going to look at this is I see 0, 0 right there, and I see that the asymptotes are intersecting at the point 4, 1, which means that this function must have moved to the right 4 and up 1, which actually tells me quite a bit already. Since the asymptotes cross at 4, 1, I know that this has to be x minus 4 in the denominator in order to get that shift to the right 4. And then I've got plus 1 out here to show the movement up 1. And then the last thing I need to do is figure out what a value goes up here. I know it's some number, some whole number, but we need to figure out what that is. And how we're going to do that is I'm going to take a look at where the asymptotes cross, right here. Then our trick was, if you move to the right 1 unit, count, do I have to go up or down to get back to one of the branches? And in order to get back to this branch, I have to go up 1, 2 units. So that means the a value in the function is 2. So I'm going to go here, and that means the equation that gave us this graph was y equals 2 over x minus 4, and then plus 1. Okay, so where do those asymptotes move, and what's the a value on top is basically what we have going on here. So a little bit of new vocab today is, and what we're going to start with is functions that are continuous. When you think of continuous, I want you to think like, could you draw the entire graph without picking up your pencil? Okay, its technical definition, and this isn't even really technical, is functions continuous is if it has no jumps, breaks, or holes in the graph. So like I said, if you can draw the entire graph without picking up your pencil or pen, then that graph is considered continuous. So these three are all examples of continuous functions. Okay, those are the equations that go with them. We haven't studied the third one, but that's kind of what we're going to be getting into, is some of these crazier functions that have x on both top and bottom. So continuous, no breaks, holes, or jumps. What that leads us to are functions that are discontinuous, meaning functions that you can't draw with one pen movement or one pencil movement. You would have to pick up your pencil at some point in time. And if a function is not continuous, we say that it has some sort of discontinuity. Okay. So if a function has some sort of weird jump in it, that's what we call a discontinuity. There's a few other types of discontinuities, but what we're going to focus on in Chapter 8 are holes and asymptotes. Okay. Asymptotes you're already familiar with, right? If I've got a graph that has a vertical asymptote, let's draw this a little bit clearer. If I have a vertical asymptote, like those reciprocal functions that we just saw in the warm-up, that is not continuous, because the one branch, I then have to pick up my pencil or pen to draw in the other branch. So that's one example of a discontinuity. And another one that we're going to get into is a graph that looks something like this, and this is nothing specific. But if you have let's say you have a parabola, but then there's a hole right in the middle of that parabola, and after that, like the rest of it looks the same. So we'll see what this looks like. Don't get too worried so far, but these are the two sorts of discontinuities that we're going to focus on: are holes and asymptotes. Now, while they look different, both of them occur when the denominator is equal to 0. Okay, so this is going to be the big thing today. If the denominator is equal to 0, there's some sort of discontinuity, whether it's a hole or an asymptote. Okay, so just want to show you an example of some of these, and I'll use Desmos in a minute to kind of help illustrate this. If you have a function that looks like this, so y equals x plus 3 times x plus 2 over x plus 2. The domain, we know the denominator can't equal 0, which means it already has the word domain. That means x cannot be negative 2. But what's going to happen is this graph actually makes a hole. At negative 2, there's going to be a hole in the graph. And the reason is because a hole comes from what we call a removable discontinuity. And in order to be removable, all that means is that factor, that x plus 2 in this case, shows up on both the top and bottom of the fraction. And if that's the case, I can essentially cancel this out and simplify this into y equals x plus 3. Okay, and we know what the graph of y equals x plus 3 looks like. That's just a straight line that starts at positive 3 and goes up 1 over 1. Right, that's just a point, or y equals mx plus b slope-intercept form. Okay, so what I want to show you is the difference between these real quick. So if I type y equals x plus 3, okay, there's my line. Right, as I go along here, I can trace the coordinates. At 0, it's 3. At negative 1, it's positive 2. At negative 2, it's positive 1, and so on. Now, if I type the function that we just had, which is x plus 3 times x plus 2 over x plus 2, okay, you'll notice that if I take the red one out, this is the exact same graph. I can switch between blue and red. Okay, they are the exact same thing. They sit right on top of one another. The difference is, and Desmos, the only place it fails is that it doesn't show us the hole in the graph. If I go to negative 2, Desmos tells me it's undefined. And of course, the reason it's undefined is because if I plug in negative 2 for x here, I'd be dividing by 0, and that can't happen. So these two graphs are essentially the same. The difference being the one in blue, this fraction on the bottom, has what we call a hole. But it is removable, meaning you can't really see it in the graph. You just have to understand that there's going to be a hole in this. So what we could do here, and you're not going to worry about graphing today, but if we're graphing this, what we would do is make an obnoxiously open circle like that, just to show that there's a hole in that graph. So holes are what we call removable discontinuities. Okay, and then a non-removable is what we've already worked with, and that's a vertical asymptote. So here, if you see x plus 4 over x minus 2, I know that x cannot be positive 2, because of course if I plug in 2 for x, I'd be dividing by 0. That x minus 2 does not show up on top and bottom, right? I have an x minus 2 down here, but there's no x minus 2 up top. We'll get into this later in the chapter, but you can't just cancel out these x's, okay? If you want to think of it like this, the only way to cancel out x minus 2 is with another identical x minus 2. So this is the Desmos made graph. This is what the graph looks like if you type it in. And of course, the asymptote isn't shown on here, but I can draw in the vertical asymptote, and you can kind of see that those branches are heading towards that vertical asymptote. Still a discontinuity, because in order to graph this function, I would have to I'd have to lift my pencil off the page. But that's just an example of a discontinuity that is not removable. Okay, so what we're going to get into today, and this is going to kind of be a lot, and I told you we have multiple days to look at this section. What we're going to do is we're going to write down all these characteristics on the left side of a function that looks like this: y equals x plus 3 over x squared minus 4x plus 3. We're going to always start with the domain, and in order to figure out what the domain is, I need to know what values of x will make the denominator 0. And that's tough to do if it's squared. So what I'm going to do is I'm going to factor the bottom. Okay. So x squared minus 4x plus 3, I want to find factors of 3 that add to negative 4. In this case, I have x minus 3 and x minus 1 is the factored version of that bottom equation. So like these things right here are equivalent. These are the exact same thing. They are identical. So anything that's true for the factored version is true for the original. So from there, I can see that the domain says x can't be positive 3. That's a weird 3. X can't be 3 or 1 because either one of those x values will make a denominator of 0, which means that those are what we call the points of discontinuity. Okay, so x equals 3 and x equals 1 are both some sort of discontinuity. And for what we're studying, it will always be either a hole in the graph or an asymptote, specifically a vertical asymptote. If we look at this now, can I remove either one of the discontinuities on the bottom? Can I remove either x minus 3 or the x minus 1? And by remove, I essentially mean, can I cancel either one out? Since neither one of those will cancel out, what I have here is two vertical asymptotes. Okay, so I would say there's a vertical asymptote at x equals 3 and a vertical asymptote at x equals 1. So both of those x values are things that I can't remove, and they are inputs that will create a line that we can't cross. The last thing that we're going to do to add on to this is we're going to figure out where are the x and y intercepts. So if you think about where is an x-intercept, that means where does it cross the x-axis. And the implied meaning here is that the y value must equal 0. Okay, and then the y-intercept, which is actually usually the easier one, is the opposite. Where is the x value equal to 0? Or what is the y coordinate when x is equal to 0? So I'm going to start with the y-intercept first. Okay. So to find the y-intercept, I'm going to rewrite the function. You don't have to do this. X minus 3 times x minus 1. So in order to find the y-intercept, I'm going to actually make x be 0. So I'm going to take and put in 0 for all of the x's in the entire function. Okay. So now this is what I need. It's solving, but it's really just simplifying. And so if I look at this, 0 plus 3 will give me a numerator of 3. And then on the bottom, I have negative 3 times negative 1, which is positive 3. Okay. And 3 divided by 3 is 1, which means that the y-intercept of this is going to be at 0, 1. I'm just going to move this down so I have space. Okay, so this is the y-intercept, or where the graph crosses the y-axis. To find the x-intercept, I need the y value to equal 0. So what that means is I'm going to take and plug in 0 for this y value. So I have 0 equals x plus 3 over x minus 3 and x minus 1. Okay. In order for a fraction to equal 0, the only way for that to occur is if the numerator is 0. Okay. If you are dividing two numbers and the result has to be 0, then the top number must be 0, which means to find the x-intercepts, I'm just going to take the numerator and ask myself what x value will make 0 here. And as we can see, it's going to be -3, which means -3, 0 is the spot where my graph crosses the x-axis. Okay, so x-intercept, y has to be 0, y-intercept, x has to be 0. I'm going to put this into Desmos. I'm not going to ask you to graph this today, but I kind of wanted to show you what this all looks like. So our original function was x plus 3. Is x plus 3 over x squared minus 4x plus 3. Okay, kind of a crazy looking graph here. It's actually got 3 different branches. And as you can see, we have x equals -3. X equals 3 is one of our vertical asymptotes, as well as x equals 1 is another vertical asymptote. And so if I change these into dotted lines, we can kind of tell. It'll be a little bit clearer that those are asymptotes themselves. So I could scroll up forever, and that function won't actually cross there. But then I can see, and Desmos does a nice job of showing this, I have -3, 0 is my x-intercept, and 0, 1 is my y-intercept, which is all information that we're able to find without graphing. So lots of stuff. I understand it's a lot in one problem, but this is what we have multiple days to look at and work on. So we're going to just keep hammering practice with this stuff. But these are the five characteristics that we want to start with. So kind of just a rundown. We're going to factor both sides of the function, determine the domain. If a value is not in the domain, so if x can't be a certain number, that is what we call a point of discontinuity. We're going to simplify anything if possible, and then you're going to determine if each POD, point of discontinuity, is removable, which makes a hole, or is it non-removable, which then makes a vertical asymptote. Okay, and then finally we have this new stuff. The x-intercept is where does the numerator equal 0, and the y-intercept is where does what happens when you plug in 0 for x, essentially. So we're going to look at 2 more of these and wrap this up. Again, I know it's quick. I know it's a lot, but just stick with it and try and do your best here. So the first step that was there is I'm going to factor top and bottom. If I look at this function, y equals x minus 5 over x squared plus 1, what's crazy is neither side of this actually factors. Just real quick, if this was x squared minus 1 on the bottom, that would factor into x plus 1 times x minus 1, because those two numbers multiply to -1 and add to 0. The problem here is if I'm trying to factor this thing on the bottom, I need 2 numbers that multiply to 1 and add up to 0, and that actually doesn't exist, which means this thing can't be factored. And if this thing can't be factored, if we look at the denominator, that also means that x squared plus 1, if I ask myself, what x values will make 0? Where are my points of discontinuity? I actually don't have any, because if I go ahead and solve for x here, I don't have, we're not going to deal with imaginary numbers, and so I can't square root -1, which means that this thing doesn't have any points of discontinuity, because the denominator can never equal 0. Okay, so this is kind of a interesting graph. The domain is actually going to be all real numbers, because that denominator can't be 0. For points of discontinuity, there are none. For holes or asymptotes, there are none, because holes or asymptotes can only come from a denominator of 0. Okay, I'm going to erase this for the time being. I'm actually going to keep that up there just for the completed version of the notes, of course. So, points of discontinuity, none. Holes or asymptotes, none. X-intercepts, remember that's where I'm going to plug in 0 for x. So this becomes y equals, it was x minus 5 over x squared plus 1. Double check that, yep. So if I evaluate this, I end up with negative 5 over positive 1, which is negative 5. Okay. So, shoot. Okay. All of this stuff, this information is perfectly great and super awesome, but this is for the y-intercept. Okay. Again, my apologies there. The y-intercept is when x is equal to 0. Okay. For the x-intercept, that is when does y equal 0, aka the numerator. So to find the x-intercepts, I'm going to say 0 equals x minus 5 over x squared plus 1. And like we saw in the last problem, this really is just asking, okay, when does x minus 5 equal 0? For what values of x? What number can I plug in and get 0 out for y? And the answer is positive 5, because if I do 5 minus 5, I'll get 0. So then our coordinate here is 5, 0. That is our x-intercept. Okay. So really this one's not as exciting because there were no points of discontinuity or holes or asymptotes, but we do have an x-intercept of 5, 0 and a y-intercept of 0, negative 5. Again, just going to kind of show you some of these different crazier graphs, just so we can see what all these things look like. This section is called rational functions. Rational function is just meaning that there's the variable in both the top and the bottom of the function. So this one's kind of a goofy little bird-looking thing, dips down, comes back up. If we look at where the intercepts are, there's my x-intercept of 0, my y-intercept of 0, negative 5, and here's my x-intercept of 5, 0. So couple interesting points. We'll get into tomorrow. This actually has a horizontal asymptote. This graph has a horizontal asymptote, but no vertical asymptote. So this would be considered continuous because I could draw the entire thing with one, without picking up my pen or pencil. Okay, last one we're going to take a look at. So we'll take a look at two more. One of them that you can try on your own. So here, again, I want to start by factoring the top and the bottom. So I have x squared minus 3x minus 4. Again, that means I want factors of negative 4 that add to negative 3. So I have x minus 4 times x plus 1 is how the top is going to factor there. And then on the bottom, I have still just x minus 4. My next step now is to talk about what's the domain. So if I'm looking at the denominator tells me that x cannot be 4 because I'd be dividing by 0. Even though that can be removed, I still have to talk about domain first. So x equals 4 is a point of discontinuity. From here, I see that I can remove the x minus 4 and rewrite this as just x plus 1. Okay. Which means I have a hole in the graph. A hole at x equals 4. Okay. And then finally what I want to do is find that same x and y intercept. So again, for the x-intercept, I'm going to let y be 0. So I'm going to put in 0 for y. The nice thing is I can use the simplified version. Now that I've addressed the fact that there's a hole in the graph, for the rest of this problem, I can use the simplified version of just y equals x plus 1. So here, I want 0 equals x plus 1, which means that what value of x can I plug in and get 0? That must be negative 1. So that means my x-intercept is negative 1, 0. Okay. For the y-intercept, that's in reverse. I'm going to plug in 0 for x. So here I have y equals 0 plus 1, which of course would become y equals 1. So 0, 1 is my my y-intercept. Okay. So these are the characteristics of the graph. I've got a hole at x equals 4. I've got 0, 1 as my y-intercept and negative 1, 0 as my x. Again, just to see what this looks like. The function was, the original was x squared minus 3x minus 4 over x minus 4. So I can see I have what looks to be just a straight line. Starts at 0, 1, which we already had, has an x-intercept of negative 1, 0. But what you can't see on here is if I go to negative 4, positive 4 is where the hole's at. So if I go up here to positive 4, it looks like it should be at 4, 5, but that spot's actually undefined because I am dividing by 0 at that number. So there's what that one looks like. If you want, go ahead and give this last problem a shot. I would recommend you try it, and then we'll wrap this up. So first things first, I need to factor the top and the bottom here. So I'm going to find factors of 10 that add to 7, which are 5 and 2. And then I have to find on the bottom factors of negative 14 that add to negative 5, which are x minus 7 and x plus 2. Okay, so the first thing is just to rewrite it, factoring anything that I can. Now the domain tells me, remember domain coming from what numbers make you divide by 0, because those are the numbers that are not in your domain. So in this case, 7 and negative 2 are my numbers that are not in the domain, which means those are my points of discontinuity. So there's either a hole or an asymptote at each one of those. If I take a look at this function, if I look at the factored form, I can see that I have an x plus 2 on both the top and the bottom, which means I can rewrite this as y equals x plus 5 over x minus 7. So because I was able to remove the x plus 2, that means I have a hole in the graph at x equals negative 2. And then this is the first one where I have one of each. So I actually also have a vertical asymptote. Because this x minus 7 I wasn't able to get rid of. So I have a vertical asymptote at x equals 7 also. So both my discontinuities are things that we're going to run across in this problem. Again, now that I've removed the holes, I can use the simplified version for the rest of this problem, which is great because if I want to find the y-intercept, I'm going to go ahead and plug in 0 for the x and the y. Well, that is equal to 5 over negative 7, which means that my y-intercept is 0, negative 5/7. Negative doesn't matter if it's on the top or the bottom number. And then for the x-intercept, that means y has to be 0. So I've got x plus 5 over x minus 7. Again, in order for a fraction to equal 0, the top of the fraction has to equal 0. The numerator has to be 0. So that means if x is negative 5, that will give me a y value of 0. So I've got simplified version, I've got my asymptotes, and I've got I've got one hole in the graph and one vertical asymptote. Eventually, we are going to get to you graphing this on your own without the help of Desmos or a calculator, or at least to get the skeleton of this. But for now, I just want to show you what this looks like. So be our last thing. We'll wrap this up. So we have y equals the fraction x squared plus 7x plus 10 over x squared, fun little graph, minus 5x and minus 14. Okay. And so sure enough, I see that if I put in x equals 7, that gives me, I can then see the vertical asymptote, which can be kind of tough at times. So there's my vertical asymptote, and then the hole was at a negative 2 value, and sure enough, I see that at negative 2, the graph is undefined. There's my y-intercept of 0, that is negative 5/7 as a decimal, and then negative 5, 0 is my negative 5, 0 is my x-intercept. So again, a lot of information in this first lesson, but that's all the things that we have to cover. Right now are these 5 characteristics. We're going to add a 6th one in the next lesson. but for now we'll start with this. So the homework is from 8.3.1. You don't have to do any graphing. Don't worry about that, but I would recommend you use Desmos to check your work.